we've got Riona and Vishnu, who are electrical and mechanical leads respectively. We've also got Maria, who couldn't make it tonight, but she's our main operations lead, and she handles a lot of the administration and organisation of the team. Then on to the other fun stuff. We've got our other departments, our R&D based ones. So we've got biomedical compliance, which is really what you guys do, where it's like we try and validate our device and make sure it's compatible with the body's physiological systems, making sure all the materials we use are compliant. They abide by the regulatory agencies that govern different regions. And also investigate a lot of interesting stuff that sort of does break those rules. So I'll go into it later, and Iman from the team will actually explain some more, but like sort of seeing what materials we can implant in the body, what new methods of reading physiological data hasn't been done before. So yeah, a lot of cool stuff there. Then we've got our more core direct R&D team. So we've got our cardiovascular simulator. We've renamed it to cardiovascular systems now, but this is called CDS. So that's our biggest sub-team at the moment. It's about 15 people in it, and they're really involved with the actual casing of the heart, where the blood actually travels through, what interacts with the blood to push it. So really, when you think of artificial heart, that's sort of the team's sort of picture in terms of like the physical scale of it. And it's the one I'm sort of most involved in just because of the mechanical nature of it. We don't have our electrical teams, so we've got controls, motor, and power. So controls is sort of in the name. It's sort of how we control the heart. So seeing if the body needs to output more pressure due to different responses from the body. Getting some data if there's any like concerning signs in the body, such as if there's increased hemolysis, if there's other enzymes that you're detecting that you shouldn't be. They're sort of trying to acquire that data and seeing how we can change the flow of the heart. We then have motor and power. So motor is more involved with actually driving the driving the pumping of the heart. So ensuring that we have like a very efficient pushing of blood around the device. And also ensuring it's very efficient, just to maximize the duration that the patient can actually use the device whilst not being connected. And then finally, power. So I guess a good segue into that. So you wouldn't really have this device if you didn't have a way of safely powering the device. So it's really important not just to sort of plug it into a wall outlet or even just like say, all right, AA battery, all done. There's like a lot of things that go into it. It's probably the hardest team, or probably the most one with the most boundaries, because there's a lot of regulations regarding how you have to power it, where you locate the battery, what type of battery you can use, and also a lot of requirements for, okay, how long can the battery be supplied, how reliable it is. I could go on about it, but they've got a really hard job, and they've been making a lot of progress with regards to, instead of just plugging yourself into a wall, you can like have a wireless energy transfer, which is really exciting stuff, and yeah, they're making a lot of great progress there. So that's our departments. I guess about the composition of the team, we've got a pretty good split amongst all disciplines of engineering. Main ones have to be with biomedical engineering, mechanical, electrical. I take it back, mechatronics actually bumped up this year. But these are just really, just like core, obviously really core departments in our team, because you really just need that really in-depth knowledge from mechanical, that in-depth knowledge of electrical, and the ones that can do both. Just to make sure everything really is cohesive and works together. So yeah, that's us. So I'm going to go into a bit of detail about how, I guess what goes into an artificial heart and designing it. So I guess an artificial heart has different definitions today. If you maybe asked the question 40, 50 years ago, it was definitely something that replaced the entire heart. And it was I'll go into history later, but it was pretty like end stage. If all else fails, this is what we've got. So it was really just like supporting patients, into like a transition phase, to death basically. It was just a way to experiment the technology. It wasn't really, it was aimed at sort of, full use across like different cohorts, but it really was just a way to, just like build it and then see if we can get something out of it. But nowadays we have a lot more purposes for it. So you've got oxygenation therapy, which is still one of the main uses. You then got bridge to transplant. So for patients awaiting a donor heart, and if they're healthy enough to survive for a period of time, they actually implant an artificial heart, and then later down the track, once they get the donor heart available, they actually transplant it back in, and they just sort of go through that process there of recovery. And then obviously there's So the mix of both. So there's a permanent solution where for patients maybe there's just like a very high risk, or I guess the benefit isn't really seen as much in patients like to get a full heart transplant. So they go with the intermediary option, which is getting the artificial heart, which is actually meant to prolong them quite a long time. So it's not really aimed at saying, okay, to make you comfortable or for palliative purposes. It's more for like actually prolonging their life. So there's a lot of ambiguity with artificial heart in the sense that is it totally or partially replacing? And it's a bit of both. So sometimes you can have a total heart replacement, which is what we work with. It's what the entire competition that we're part of actually focuses on. But you can have a few different types. So you can have ventricular assisted devices. So they're more based on actually assisting with ventricular contraction, or if there's like a very low sort of diastolic function, you have that as well to add to help out. And that also only like focuses on one ventricle, so usually it's the left one that fails, just because that's the one that's pumped stronger. And yeah, so that's sort of like the main sort of first stage, like band-aid, like trying to see, okay, if it's just the left ventricle, let's just fix that one. No need to replace the entire device, entire heart. However, if you have both ventricles that are diseased, or you have some very, if there's like, for example, lipid consolidation in different parts of the heart, or if there's like, if there's very disease, due to like poor diet, lifestyle, then you could go for the total artificial heart, which is, what we're aiming to develop. So, the first generation artificial hearts were made before we even got to the moon, which people kind of like, struggle to comprehend, because if you imagine how far we've come from like the first moon landing to now, where we're like recycling rockets, and compared to artificial hearts, where we now have a full competition saying, okay, fix this for us, because it's quite hard to design. So we've gone through a few generations of artificial hearts trying to see if there's differences we can make, or if there's improvements we can make to each iteration. So first generation artificial hearts are all categorized by the same sort of characteristics, which is using a diaphragm or using a pneumatic system, so being able to create the pulsations using compressed air. So you'll have all these artificial hearts will have a form of like a pneumatic system where it will just circulate the pumping of air, and that will create the pulsations in each ventricle. So you have the very first one on the left. So that was from 1969. It was developed for a lot longer. It was, I think, 1964, 63, when it was first sort of developed. But it was implanted in 1969. I think it was the first official one, and it didn't really last very long, just because there was high degrees of hemolysis. So that was using the same system that I mentioned, but it was using different sort of linking. So it was using dacron, which is just a type of material that the ventricles are made of. And we basically didn't have too much progression. Like, this was the main sort of mechanism for all these devices moving forward. So you had different brands, different universities come up with different ones. But then you had the Akuta 3, which was actually quite fundamental. So it changed up the valves it used. So obviously an anatomical heart has like tricuspid valves, mitral valves, all these different types to regulate the blood flow. For the Akuta, they decided to change it. Instead of using the disc valves, which I can show you an image later, but they used a different material as well, and the hemolysis was actually quite reduced this time around. So the problem with heart valves is that they can create a lot of shear on the blood, especially after repetitive use, and that just promotes the hemolysis throughout the bloodstream. So with the Akuta 3, it was actually found that the changes they made reduced it significantly, and it was quite influential. But then you have probably the most important one out of every generation, the Jarvik 7, because it's the one that's actually still seen today. Not exactly the same, but the idea was it's the first FDA-approved artificial heart. Back then, I think it was a lot easier to get this stuff implemented, just because there was very low, barriers for entry, a lot less, was known about the potential of these devices, and they were very breakthrough at the time. So it wasn't the restrictions weren't as bad, strict, whereas now it's sort of a lot more hard to get into the market, and that's why it's been so successful, because getting this FDA approval is quite difficult nowadays. So the company was actually bought out by several, and now it's currently Syncardia, which is the main developer of these devices. You'll see them later on. The longest survival for one of these was 620 days, which for back then, and considering it was about 13 years since it was first explored, it's quite impressive. So it opened up the idea that destination therapy is just no longer the main use of these devices. You can actually use it for other purposes, such as a transition period to an anatomical heart. We then started moving on to different generations. So second generation was just a very big improvement of the first one. And it was mainly using just different pumping chambers. This is an reiteration of the Jarvik 7, just as you saw before. And it's currently the only FDA-approved device at the moment. So considering from 2001 or even 1980 to now, we only have one FDA-approved device. It's quite, shocking. There was another one called the HeartMate 3, but it did get recalled, I think 2-3 years ago, just because it had a lot of issues regarding hemolysis in one of the sections of the device. So even if it was just one section of the device, if it was just like a small defect, they had to recall the entire device, and it really was quite frustrating in terms of progress. 1,500 patients have so far received the Syncardia artificial heart, with 80% of patients living long enough to receive a heart transplant. So that's become quite a dominant purpose and use of this device as well. So we have like the pneumatic compressor that I mentioned before, but it was a lot more improved. Like, think about it, 6.1 kilograms total weight at the moment compared to the Jarvik, which was basically 2.5 of me, which is quite scary. So it delivers 3 hours of charge, which you can imagine might not be too much, but it sort of, I guess it does the job pretty well, and they are trained very well to use it in that time period. Not to mention that it's also all included in the backpack that is external to the body, and patients have said that it's been pretty comfortable. In fact, the main complaint with these devices is the noise, because they find it hard to sleep at night with them. And also, I think just overall the burden of having to plug yourself in every night or plug yourself into somewhere, or the fact that to think about, if I get a flat tire, I could die, which is quite scary. So yeah, there's a few things that still trouble the device, but it's really shown the test of time overall. Third generation's a bit of a weird one because we still have those pulsatile pneumatic systems, but at the moment we are looking into very new implementations of the device. So we have basically total implantable technology. So at the moment we have these pneumatic drivers which are external to the body, and they pose a lot of issues, such as, well, first of all, having to carry around these devices on your hip or on your back, the risk of infection due to the entries to the body being susceptible to different bacterial infections. And of course, so that the use of this technology is quite important, and it's actually being used in a lot of devices today. And also, you actually have the issue is you have, it'd be much harder to replace components, because external devices, it's pretty easy. You just sort of swap it out, put it back in. Whereas with totally implantable technologies, it's very difficult to do, and in some cases could be fatal if it's not done properly. Another component is continuous flow devices. So at the moment we've sort of covered pulsatile driven, so how your heart normally pumps. Whereas with continuous flow devices, it's more like using a pump that you see everywhere. Like, if you have to go to a tap and just turn on the faucet, the way the water would come out would be because of a continuous flow pump. So that would be just using like a rotary vein, and that would push blood. At the start, it was pretty controversial because it damages blood significantly more, but over time, we've actually seen improvements in the technology, and it's the one that's sort of been making the most buzz in terms of durability, performance, weight, implantability, and overall reliability from the pumping perspective. And of course, long-term implantation of these pumps is still quite a debated topic, just because you've got to be careful of sort of just like how long you can stay with this device in terms of like hemolysis impacts, downstream organ as well. So and then the third technology, which is sort of a quite novel concept still, is magnetic levitation. So the stuff you see on trains in Japan or in other parts of the world where they're just where there's like very minimal friction and heat losses, you can actually see that with artificial hearts as well, where they actually have that vein or impeller, what we call it, being floated or suspended in the device itself, and it's actually been quite successful with like heat losses. I guess the question is stability over time, and also the cost to the user, because it does get quite expensive. So this is what I was mentioning before. These are the two main third generation pumps. So some of you may be familiar with the Vivacor one. It's the one that's been making most headlines now. And they've got a very successful design in the sense that it's very efficient, uses sort of magnetic levitation in a very innovative way, and it's also very compact. And so far, yeah, it's been approved for clinical trials in humans, and it's been very successful in doing so. Just before that, we have the HeartMate 3, which was FDA approved at one point, like I mentioned before. Has a very similar sort of structure as the Vivacor, with its very minimal sort of gaps in between the actual device and reducing that sort of flow and disruption to the overall flow of the heart. However, yeah, there was blood obstruction at some points just because of the design and the long-term use. So that was unfortunately recalled. All right. So a bit more about the team. So I've got this video here. I probably won't go through the whole thing.
Impeller with our shaftless
I just want
of our team. Our design features two adjacent reverse rotation centrifugal pumps, simulating a passively magnetically levitating impeller with our shaftless system. Our goal.
So I'll quickly just go back to that. So very similar to the Vivacor design. Actually, I'll go full screen. Very similar to the Vivacor design from a casing and driver perspective. It was a very I guess conservative option, but we're also trying to push boundaries with regards to how we're actually driving it. So on the very right here is sort of my brainchild. We sort of came up with a way to isolate the electrical components without directly impacting the bloodstream, which we felt was like a lot of the other ones, and that would help reduce the heat loss, reduce the chance of infection, reducing the unwanted contacts with different components that aren't necessarily compatible with the body. So that was our main design. It's not fully loaded, but the idea is that you would have basically two of these, and they're both independent drivers. So if you had to increase pressure on one side of the heart, you could do that, and not affect the other one in the process. This was a great design, but we did notice a few issues. Number one, this thing is giant. I've got the volute right here. I'll show you around later, but this thing is heavy and it's quite bulky with a lot of unnecessary features. Number two, we had a lot of heat losses despite our efforts to reduce the distance between a lot of the electrical components. So we had a lot of just a lot of heat loss, a lot of energy loss, not really much performance like we wanted. And that also would have downstream effects on the body. So if you have a very hot component, that would obviously locally affect the blood. That could cause hemolysis. It could raise even body temperature if it's not controlled properly, because that could spread to other components that can withstand and contain heat for a while. So this one was it was a very innovative design. We actually came second in the competition in the inaugural one in 2023. But we decided to move to a different one the year after, using a similar workflow, but significantly compacting the design. So just load it up here. So this one's a bit more elegant, but the idea is you'd have two different halves. One half would be a lot smaller than the other. In this one, it looks similar for ease of demonstration. But the left side is sort of the red impeller you can see there, and that would have a differently designed impeller to the right side, because that would pump more blood around the body. So you imagine left and right ventricles, it's very similar. Over here you have the right one, so the right one would be differently designed. It would pump a different pressure outputting curve. The point I'm making is that we wanted to condense the device entirely and make sure we only have one driver pushing both sides of the heart. So that was our main sort of output, our main sort of focus. We even pursued a different motor design, which I actually left over there, but the idea is that we really wanted to make it, I think we made it to about 2-3 millimeters, the entire motor design, and try and push that novelty, which the competition tries to emphasize. So, I've talked a lot about continuous flow devices, but going a bit back to the original pulsatile idea, there's still the very big debate of whether we shouldn't completely transition to continuous flow devices. So the main, I guess, benefit is that your heart, for millions of years now, has shown or thousands of years, I should say, but has shown, pulsatile nature throughout the entire lifespan. A lot of the body's processes are pulsatile. and require sort of blood delivered in a peristaltic manner anyway. So why change it? Why try and put all this effort into potentially causing harm to other organs? You even have evidence of reduced blood-related complications. So that includes like thrombotic events. You even have your sort of gut as well negatively impacted from artificial heart transplants. So it's important to ensure that if we are to maintain the blood flow, but it is important to maintain the blood flow for these organs to work properly. Also, you can mimic the pulse profile a lot more accurately with these devices. We've seen continuous flow devices try it, but it's not been as fruitful. And even then, we still see the same complications with continuous flow. And finally, we can also have a lower duty cycle, so we can even improve efficiency, while we can't perfectly mimic it. We can still try and figure out ways to improve it by turning off the device in certain points. Disadvantages, I guess, yeah, you have like very limited power delivery. So the problem is like if you're sort of only pushing at like a certain time, there's really very little power you can deliver in that span. So you have to make sure you optimize the timing pretty well. Much less reliable because it's a lot more mechanical. These components are a bit more elastic. They're a bit more plastic based. So you have to really, it's sort of really unknown sometimes how, no matter how well you design it, things could go wrong. The blood could interact with the material a bit differently than you imagined. So yeah, that's a very big emphasis on there. And then materials are also generally less durable and require higher maintenance. So that's why a lot of these pulsar devices are external to the body, while there are efforts to make them internalized. Just something you have to keep in mind. And also manufacturing workflow is quite complicated. So with continuous flow devices, they're very mass produced at the moment, not just for hearts, but for like everyday applications. Whereas pulse style devices are a bit more finicky. You have to have like different processes. It's a bit longer to produce and a bit more expensive as well. So these are things you sort of have to keep in mind. Another thing as well is that you need a bit more control on how the blood flows. So just like your anatomical heart, you'll need valves in the devices themselves. So it's important to make sure that the valves are properly timed to close and open. They're usually done naturally by just like normal vacuum, like if you just create a vacuum in one area, that'll close the valves and it'll open it once it's released. So it's really important to make sure these are properly designed and that they're designed with the intention to reduce shear and damage to the blood. Also, you can have it mechanically actuated to improve the timing, but once again, it has to be reliably tested. You don't have the chamber itself, so the chamber is sort of the main, it's sort of the heart of the heart, so you have to make sure that you're going to have like repetitive contractions in these chambers, that they're repeatable and that they can withstand fatigue and long duty cycles as well. All right, so Rihanna, do you want me to go through this part or?
Up to you. I'm happy to speak if you want to have a break.
No, all good. So I might pass on to Rihanna, who actually wait. Sorry, is it okay for this?
Yeah, I'm happy to talk about it.
Yeah.
Still.
Easy. Sounds good.
Yeah, awesome. So I'm Rihanna. I'm studying. So Brian is studying a double degree with biomedical science and mechanical engineering. So that's why his strength is in mechanical engineering. I'm studying mechatronics, which is a combination of mechanical and electrical. I'll talk a bit about our current design and our direction for this year. So as you know, in our 2024 design, it was continuous flow, and there are issues with that. So we want to go back to pulsatile, and this is actually a common thing found in industry as well. So there was a real big boom in the 2000s and 2010s for these continuous flow devices, but as the effects became more widely known, especially the long-term effects, there's kind of been a regression almost in literature into finding ways to do pulsatile novelly. And yeah, as you can see, our device was quite large. Like this was our 2023 device, and this is our 2024 device. And while there's a reduction, it's still quite large, and that has to fit in your chest cavity. So I might pass these around. You guys can have a look. And yeah, one of the words there, open loop control system. So your heart responds to chemical feedback, hormonal feedback, even physical feedback by where your diaphragm and lungs are, like within the cavity. With a mechanical device such as a centrifugal, like continuous flow pump, you can't do that. You can't really sense hormones. It's not really a technology that exists yet. So you're just kind of guesstimating what the best flow rate is, and that can be uncomfortable for patients and sometimes be fatal for patients. So we are trying to implement hormone sensors, oxygen sensors, and flow rate sensors into our device. That way we can have a better idea of what is happening in the body at a given time. And lastly, you guys as doctors or future doctors and future MedTech designers just kind of may take for granted that all the devices you use have been tested and trialed on people throughout history. And these clinical trials with animals, humans, people sacrifice their lives to make sure you're using a really safe device. And we're trying to get better at doing that without using biological clinical trials. So we're trying to improve the way we can simulate the human body and therefore hopefully get a better device out of that before going into clinical trials. And yeah, some of the positives of our 2025 design can be seen here. So a pulsatile system reduces stroke, less chance of hemolysis, less chance of thrombosis, therefore less chance of a clot going to the brain. Working within the actual physiological dimensions of the thoracic cavity means that it's easiest for us to verify against CT scans if our device will fit. I've mentioned responding to physiological feedback, but as well as increased quality assurance, which is all about the FDA, as Brian mentioned before. FDA applications these days are millions of US dollars, so you want to make sure you're getting your science right before you apply to the FDA and say, hey, I've got this idea. So that's kind of where we're trying to head. And I think another thing with our device and something we want to take into this year as a kind of cutting edge factor within the competition is increasing accessibility. So a typical medical device tries to target a specific cohort patient. Patient cohort. So in history, that has been adult male 65 large. So that completely removes any other size person from the equation. So women, children, growing people, sometimes they're automatically excluded from devices just because of things they can't control. So by increasing accessibility for patients, we mean all patients. So the first point is an engineering thing. So by creating our device out of materials and systems that are closely matched the final device, we're reducing this R&D cost, which means that it will be cheaper for the patient. Keeping serviceability front of mind, so it doesn't just end once the surgery is over. These patients have to go back to clinicians. If you're a clinician, you have to manage this patient's care, and if you don't know how your device works, or you can't control how the device works, then how are you going to give the patient the confidence to also do that? So I think we're trying to make it easier for clinicians and patients to use. Lastly is designing for reusability. So a big thing with pushing towards net zero is how can we minimize our effect on the planet, including greenhouse emissions. Some hospitals now, what they're doing is kind of a buyback system. So it's a bit morbid, but if a patient has died with a device in them, hospitals will often keep that and sterilize that device, not to be reused, but to be used for testing and development. So by making our device as sterilizable as possible, we can kind of reduce the cost there and make it, less impactful on the planet. And yeah, we've got a video here of our current device. Is there a specific time?
The pulsatile flow system uses a flexible membrane using silicone injection molding. The membrane will move back and forth to replicate the physiological flow of the human heart's beating action.
So I'll just pause there. So there's a lot of engineering words there, but your heart is a muscle that flexes in and out to pump the blood, and we're trying to recreate a membrane that does that and a drive system that does that. So it is more similar to what the actual heart does, and we're hoping that this puts us above the competition in terms of actually producing good outputs for the patient. I'll move on to the next slide unless there's anything else I should cover from the vid. Yeah, so here is a detailed overview. basically that big gold system in the center that provides your drive. So in your actual heart, the electrical signals stimulate the muscles to contract. Instead, what we're doing is using a motor to contract, move these pistons up and down, which will then contract and displace the membrane. And what this does is create pressure changes, which is very similar to your actual heart, and blood will flow in, and then once it's pushed up, it will push out. And what we're doing is converting the continuous motion of our motor from last year into pulsatile action by using, it kind of looks like if you like cars, like a differential. I'm not too sure about cars, but kind of going back to other engineering disciplines and seeing how we can improve our device that way. And yeah, something that might interest you guys is that all of these devices have pre-clinical testing, and that is what can the engineers do to simulate the body and simulate the conditions that the device will be in without actually having to rely on animal testing and things like that. So what we're developing is a mock circulatory loop, and that simulates the different pressure changes throughout your circulation system. So it has the two halves. Maybe Ryan, I don't know if you want to talk a bit more about this or if there's anything you want to add.
Yeah, sure. So like Rena said, this is a way of testing it in sort of the benchtop testing. So I can do it right here. I can just plug everything in, all the outlets, get our measuring software, and we're good to go. The thing is that we can really advance these testing, like these rigs, to like a really big extent, which is why they're so popular in different universities and departments. So the idea is you can adjust the pulmonary resistance, the arterial resistance. If the body's got sympathetic or parasympathetic innervation, then how can we adjust the simulation or the loop to account for that? So it's quite important. It's quite an important way to see if our device can meet all those needs and if there's anything we need to improve on. Yeah, there's a lot of technical stuff there, but I think the real point is you can really get a lot out of this, and ensuring that whatever you design is just as closely mimicked in your, closely mimicking what's happening in your body as much as possible. Yeah, I think there's an electrical slide.
Yeah, awesome. And so going a bit back to what I was talking about before about, you as future doctors or clinicians, just accept that the device placed in front of you works. As engineers and scientists and doctors who are involved with MedTech projects, you actually have to verify and kind of build up that trust and make sure that your device is going to work 100% of the time, 100% how you expect it. And so yeah, we did have some, I wouldn't say failures, but learning opportunities last year. So this on the left is a transcutaneous energy transfer prototype. So instead of having a drive line through the skin and essentially having wires come out of like a stoma in the cavity, what we can do is have kind of like wireless charging with your phone. Like you just put your phone on something and it charges. We can do that for the body. This isn't new technology, but it's quite hard to be adopted just because, as you guys might know with your wireless chargers, if you get it off by like a millimeter, it won't charge. So that's what we're trying to develop, and we tried and we found it was only 10% efficient, which not very great. I think if your heart was only running at 10% efficiency, I don't think you'd appreciate that. As well as it was quite bulky. We're all undergraduate engineering students, so we're just kind of feeling it out as well, which is, I guess, the great thing about the competition. And I guess MedTech competitions or programs like this, you can really feel it out and you're allowed to make mistakes, and people's lives aren't like on the line, or people's money isn't on the line, which is great. As well as our motor. So a lot of the energy is lost as heat, which means that the motor is not efficient. And a motor in a heart will be pumping or like spinning continuously. And this is not just for a few days, this is for years. And we want to make sure that our motor can spin continuously for years. So we decided we need to go back to the drawing board. And this is a bit more technical, but what we're using in our device is called a PCB motor. So your typical motor, when you think of an EV, we use the same technology essentially, but in an EV, you've got physical, I guess, windings, and these kind of look like, orange copper, like wound around you. Maybe look one up if you're not too sure, but they're huge, right? Like, the ones in EVs are like this big. And with anything made out of any material, there will be issues with that material, and materials aren't perfectly made, so energy can be lost that way. And what we're doing instead is minimizing the material that goes into our motor, and therefore increasing the material efficiency of our motor. And that's quite a big, I guess, point in motor design. So this is a relatively new application. I'm not doing it justice. Maybe I'll go back to it later if you are like wanting to know more about it. But cut a long story short, in a typical motor, you have to laminate it, you have to wind it, you have to create end brackets for it, and you have to have a fan. In a PCB motor, you remove all these points, and therefore you cut around 86% of a motor manufacturing's carbon emissions. So this is great for the environment. We're using less materials, we're emitting less carbon in the process of making the motor, and I think that's something that we are all going into the world, like we'll be on this planet for 50 plus years, and there's a big push towards recycling things, and I think it starts with us, and I think medical devices are moving towards being able to be recycled, like medical pantry, things like that, like making sure things don't go to waste. So that's one way we're innovating in our device. And from an engineering perspective, we can actually simulate things without building it. So that's another really good thing. But I don't think it's too inaccessible. I think the whole idea is that all these softwares, while they may be hard to uptake at first, they really cut down the time you spend developing your device, which is good for a money perspective. As you can see on the left, that's our 2024 motor. On the right is our 2025 motor. And this is one of the rigs we're developing to simulate the conditions that the motor will undergo in the heart. So our idea is to run the motor for as long as possible and see when it fails. And then, we can tell the FDA, well, our motor will run for, 8 years with maybe like a 90% confidence. And, that's like pretty good. And going finally into the control systems. So as I mentioned before, in terms of medical devices, now with the emergence of AI, people are looking more at the algorithms behind the devices and how they can take physiological data and interpret that and provide a meaningful output to your medical device. So we're not using AI, but what we're using is more sensors, so different types of sensors to try and get more data. And then the idea is that we can optimize our algorithms to produce a better outflow for the patient. I might just skip this. This is our TET. So if anything, this right graph here, you can see here, so at a separation distance of 4 millimeters, so assume that the coil inside your body and the coil outside of your body is at a distance of 4 millimeters, we achieve around 93% efficiency. As you guys know, the human body doesn't have skin, it has like a fat layer, that can be up to 12 millimeters between the cavity and the outside. So we've got quite a lot of work to do to develop that into actually matching the physiological system. And our future work for this year. So our competition, our finals are in Vienna at the end of the year in December. So up until then, we'll be working towards getting results, showing how efficient our design is, really putting in that science side and making sure that we can deliver a device that confidently does what we achieve, like what we set out to do. So that includes validating simulations, doing smaller simulations, manufacturing things, and doing some testing, all done on campus here. So it really is a testament to all 42 members. So we're all undergraduates, it's 42 of us, and we're just kind of working together and trying to learn and produce a device. And that's kind of the essence of Monash Heart Hack. I'll hand over to Brian to talk more about anything else.
Sure. Yeah, hello everyone. So thanks for making it through what seems like about 40 minutes. So sorry for going way over. I didn't want to take away from the prosthetics part, but yeah, I think it's a real important student team. There's not many like this around. You've got the really big ones, motorsport, the rovers, but really this stuff is some of the most challenging in engineering, trying to balance out biomedical, a money perspective, everything. I like to think of artificial hearts more like a balloon, or a bunch of balloons in like a water stream. And the aim is to like push the water around and the balloons around without popping them. And if you pop like 2 of them, you lose. So it's really annoying, but it's also quite a fun challenge to work around. So yeah, thanks everyone for listening. We'll take any questions if anyone has any. That's not a question, but sure, I'll take it. Thank you very much, really.
Also, not to single out, but we've got Aman, who's our compliance lead. So Aman is studying biomedical science and she's currently doing her honours, I believe. Next semester, she's starting her honours, which is awesome, and she handles our, being compliant with the clinical aspect of the device. So if you had questions for her as well.
Sorry, I didn't catch that. What was it?
The artificial heart that you guys designed has pistons and such, right?
That's correct, yes.
To make possibility. What's the whole point of the biopore going to have one moving part to make it to cut down on the number of hearts that fail and maintenance?
No, that's a great point. I think the problem is, not the problem, one thing they're trying to do is cut down the amount of moving parts, but also, you know what, I just pulled it up. Bivacor has a really interesting system where the impeller is right bang smack in the middle, and the way that they alter the pressure is by basically first in changing the speed, but second changing its position vertically. Not vertically. I guess like how far it is to the left or right side of the heart. So let me just try and see. I think it's the device. It could be somewhere deeper. But the idea is, it's a great video. That's okay. So the idea is that this spinning part here actually just only, like it's basically just like wedged in the middle, and there's nothing fixing it because it's a magnetic levitation system. So something we noticed, first of all, trying to achieve this is very hard, especially with like, from a student perspective and with the materials we have access to, we just can't really achieve this level of
I'll actually add that in 2013, when Bivacor started, they bought their motor design off a Japanese university that had been investigating this motor design for 10 years. So Bivacor has been in development for like 20 years. I think that's the big thing with medical devices, is that a lot of knowledge and time and effort goes into them to get them right. And we're undergrad students, I don't know. We just try and do what we know will work within our capabilities.
Yeah, it's definitely a great solution, but it has its questionability of like how reliable is it in like an everyday patient perspective, just because how reliable or how sure can you be that this floating disc can stay in that position, and if it bumps up a few millimeters because let's say I jumped, like how well will it like center itself and not hit the wall, and then that will bang itself around and then I will just collapse on the ground. So there is a lot of like, insecurity regarding it. Also, it's very, very early. Like this started development in 2010, even earlier, I'd say like 2005. So it's 20 years in development, this entire device, and they've only just gotten to human trials, which is, sort of like pretty short if you consider like artificial hearts anyway, but also it's something that you just can't really, it's just like something that you really need to like try as much as you can to ensure it's stable. Sure, our device has its drawbacks of having more mechanical components, so that's something we acknowledged and were willing to accept. I think just the main point is how well can you design it, and what new materials can you try, because it's one thing to design this sort of product here and sort of say, okay, yeah, it's continuous flow, there's no moving parts, whatever. But it's another thing also to say like, what if we take these pulsatile piston like designs that previously existed, and let's say we push them to the like furthest extent that we can. I think I've reached the point of the video where it might. It usually shows you how like it actually manages it. Yeah, so it is quite a fascinating device, and it is very impressive, but also it doesn't single out, I guess, everything before it, because we really need to try and like see, okay, what have we really exhausted all the resources for this other technology? But yeah, hope that answers your question. Actually, here it is. So you can actually see really quick. So you've got the left and right side. So left is the red, right is the blue. And the idea is that it will just basically, so both sides are by like the same, or like it's like using the same single moving component, like you mentioned. But to alter the pressure, you would actually have like a way of controlling how far left and right actually pushes. So I don't know if I'll mention it. But also, yeah, you see this, like, imagine your blood going through that. You know, it's like almost like a blender basically, which I mean has proven well in scientific studies so far, but there's really like no saying how well it's going to go until we sort of do a much larger scale trial and we start seeing maybe the potential downfalls of it, like we've seen with other devices similar to this.
Oh, and another thing to bring up is that, so with the Generation 1, Generation 2, they're pneumatically driven, which means they're driven with compressed air. And you cannot have compressed air or compressor inside of your body. There will always have to be a line coming out of your body. And so our idea using the pistons is that it's a pulsatile system that is internalized. So, you know, I think as, university students, you have the freedom to explore things in depth, I guess, a little bit more than if you're in a real company. And that's kind of what we're, the niche we're trying to sit in is utilize the fact that we don't owe people debts. We don't, want to put people, we're not putting people's lives on the line by just trying something new.
Yeah. Also, don't forget, there is no continuous flow device FDA approved at the moment. So all of them are pulsatile driven, and that's part of why we also chose it, because it's streamlined and there's already a pathway, like a reimbursement pathway, regulatory pathway that's been followed for the last 50 years. And not saying that we're resorting to old habits or that we're not willing to innovate, but we know that we can innovate whilst using a pathway that can we can actually sort of follow. Yeah. Any other questions? No? Okay.
I've got a bunch of questions.
Oh, easy. All right, sounds good.
Sorry, could you go back to your diagram? I was just trying to wrap my head around where the blood's actually flowing through the device. Yeah, it was the diagram.
Yeah. So I think just go here. So, do you want to go to the next slide? Or
Yeah, if the cross section's even better.
Yeah, easy.
Could you just point us through how which ones, where the inlets, where the outlets, and are there valves at each one?
That's right. This is a very simplified image. This was for our render for our prelim report last month. But the idea is these are the chambers that would have where the blood would mainly come into, and these are just the travel paths for the pistons. So we'll have the motor here. It will spin these two gears. One of the main challenges of our device that we're still trying to figure out is how we can change the pressure, not independently, they're both going to change at the same rate basically, but how we can potentially have a shifting system that could shift not different gears, but we're potentially considering a different path or a different flow profile. So if we do increase the speed, we can increase the pressure with a different, it's a bit complicated. But the idea is that this is sort of a black box at the moment. We're still sort of figuring out how best to implement this pulsatile motion. But like Rihanna said, the past ones and the ones that are currently approved have all been pneumatically driven, which basically is a main improvement of our device, where we've actually improved the durability already by not using air at all and not relying on a bunch of air pushing in and out. So yeah, this would spin these set of bevel gears, these two bevel gears. I guess it might not be bevel gears in the end, but it's a good way to demonstrate what we're trying to do. So the idea is to take this rotational force and transfer it into a piston, linear actuation. These will alternate obviously because you've got the left and the right sides. The left side would be has actually a longer path, meaning you can actually deliver a lot more pressure. And that would basically lead to this chamber here, where you've got where the blood actually comes in and gets pushed out. So if we start with the right side, for example, where your vena cava connects to, so that would be also another thing I should mention. the atria might be conserved, it might not be. It just depends on how diseased the patient is. But with our assumption, I believe we are still maintaining the atria, just because if they want to get their, if they are awaiting transplant, then it can be a lot easily implanted if the atria are still retained and intact, because their replacement heart might not actually have atria retained. So that's still up for discussion, and that depends on a case-by-case basis. But the assumption is that the atria still exists. So the idea is you have like valves at the entrance, like the entry points here, and then that would just lead to like the mixing. So this would be really the only, this is like sort of exaggerated, but you could have like a lot larger depending on the patient, and that would be where the blood actually enters and gets pushed out.
Is it soft? Is that the silicone part that's soft? Is it?
It's rigid for the case of our heart. The idea is that the membrane being pushed here, which it's very hard to animate, but there would be a piston here, or a membrane connected to that piston, and that would sort of expand and contract.
Yeah.
So the exteriors would be rigid. We have explored using like a flexible casing, but at the moment, yeah, it's still sort of in the works and up in the air if we decide to go with it. I think the main point is to get this membrane to work properly in a rigid scenario, and if we need to use like a flexible casing that can contract or can change its shape, we'll sort of go from there. Yeah.
Like in last year's device, you had like the motor in the middle.
Yep.
With either side spinning. Could you do the same thing with this one? Like instead of having the gears, just have it down the middle again?
Absolutely, you could. I think the idea was so one of the reasons why we weren't doing that was to have like a force multiplier. So the idea is if you have like a direct transfer of the motor power to the shaft, to the pistons, you would have no way of augmenting the torque. So for context, if you have a small gear connected to a big gear, that would multiply the force. So you'd have like a lot more torque generated, which in this case is actually more valuable, because there's no point having a motor that goes 5,000 RPM and being directly set, having a piston that goes 5,000 contractions per minute, whatever, because that would just damage your blood. So the idea is to find a way to actually multiply the force in between. So that would be the reason of having the two sets of gears there, as opposed to having, like a direct drive. If that makes sense. Any other questions?
How are people going in terms of we have hit 7:35, so people need to leave. Also, feel free to go. If you have more questions, feel free to stick around. But maybe we'll finish it there, and if you have more questions, just come to the front and ask them. But yeah, please join me in thanking both Brian and Rihanna for coming down to present to us, guys.